Welcome, everyone, and good afternoon. My name is Naomi Fukugawa, and I am currently the director of the USDA Agricultural Research Service Beltsville Human Nutrition Research Center. I'm pleased to moderate today's webinar, which is brought to you by the Institute for the Advancement of Food and Nutrition Science, or IFNS. This webinar is approved for one continuing education credit through the Commission on Dietetic Registration. After the webinar, all participants will receive a brief survey which will allow you to access the certificate. For those of you not familiar with IFNS, it is a nonprofit scientific organization that advances food safety and nutrition science for the benefit of public health. Intellectual contributions from industry, government, and academic scientists to identify areas of common interest. Currently, I serve as an advisor to the IFNS Sodium Committee, which brings you this webinar today. This slide shows the control panel. Please note the question box, and we encourage you to type your questions here. The questions are only visible to the staff, not to the other attendees. After the presentation, submitted questions will be read to the presenters to allow for dialogue. Here you can see our program for today. This program is to understand the state of the science related to sodium reduction in foods, what technologies are in place, what progress has been made, and what more can be done. So let's get right into it, and I'll introduce our first speaker, Dr. Janice Johnson. Dr. Johnson is the Technical Service Advisor within the Salt Division of Cargill, a provider of agricultural products and services for the food industry. She will tell us about the latest in sodium reduction tools. We welcome Dr. Johnson to share her insights on the current status of sodium reduction in foods. Janice?
Thank you, Naomi. Great. Hopefully everybody can see my screen now.
Yes.
Great. Hello, everyone, and thank you for attending today's session. In my presentation, I will be presenting the food scientist perspective on sodium reduction and how the industry is making movements in the right direction. According to World Health Organization, 2.5 million global deaths are preventable if individual sodium intake is reduced to 2,000 milligrams today. To drive towards this recommendation, member states of WHO have adopted global targets of 30% reduction in sodium intake by 2025. A study by Santos identified 96 countries that have national salt reduction initiatives. This is an increase from 21 countries observed in 2014. Strategies include interventions in public settings, so think of schools, think of hospitals. Consumer education program is another strategy and may be part of that intervention one. Strategies that directly impact the food industry are food reformulation, front of package labeling, so think of the traffic lights that you see on the UK food products, warning labels in Mexico, and taxation of food products high in sodium. The initiatives are voluntary or mandatory. For instance, sodium levels in breads can have a certain limit that a food manufacturer can voluntarily meet or has to meet by mandatory. So there are a few studies that report the source of sodium in the diet, and in general, 73 to 77% of the sodium comes from processed food and restaurant foods. In some foods, such as milk, meats, and vegetables, sodium is naturally present in relatively low levels. The lowest level of sodium contributions are from home cooking and salt being added while eating. In recent years, emphasis has been placed on the food industry or the food supply to decrease sodium content in foods as a mean to substantially decrease sodium intake in the population. So when we think about reducing strategies of reducing sodium in food products from a product developer's perspective, there's basically two means. It's either reformulation and or processing. For reformulation, the first approach is to gradually remove salt over a given period. It's a stepwise fashion to actually reduce sodium. But at some point, only so much salt can be taken out of the formula, generally about 5 to 15%, before the product attributes become unacceptable. At this point, reformulation focuses on removing other sodium-containing ingredients. The next best tool for alternatives for a sodium-containing ingredient is usually their potassium counterpart, such as potassium chloride, otherwise known as potassium salt, for salt, and other ingredients are going to be used to help bring back some of the flavor that salt gives to food products. Ingredients such as herbs, spices, umami compounds, you think of those that are found in yeast extracts and mushrooms. For processing considerations, distribution of salt in the food products is one tool, and that's really about varying the level of salt within the food product itself or using emulsions that have high levels of salt in aqueous solutions. So imagine a slice of bread that looks like a layered cake. One layer has high salt concentration, and the next layer will have no salt added to that layer. Results from experiments suggest that different levels of salts create a higher salty taste response than salt that is evenly distributed within the food matrix at the same sodium content or salt level. For topical applications, when you think about chips or crackers, we can leverage the particle size and shape of the salt crystal and target one that dissolves quickly in the mouth. And what this does is give the impression that things are saltier than what they actually are. So you can get a saltier product at lower sodium level. Another trick that food manufacturers can look at is the order of ingredient addition, which can also impart salty flavor and texture of the food product. Lastly, consider modifying the operating conditions. So mixing times, so how much time you mix meat with salt, as well as temperature, cooking temperatures, to help build the desired quality and sensory attributes, be it visual, texture, taste of the food product. So as you see, there's many avenues to pursue, but finding the right combination can be rather challenging for an overall technical solution. In addition, there is more than sodium reformulation that food manufacturers are working on to meet market trends, including sugar reduction, healthy fats, increased fibers, increased proteins. All of these competing initiatives just add another layer of complexity to food reformulation. Considering the major food categories, there are many sources of sodium, including preservatives, leavening agents, flavor enhancers. Proteins can be from dairy or vegetable-based, but the most common ingredient found in all the categories, is salt. And as mentioned earlier, this is the first strategy food manufacturers use to try and reduce sodium, namely just reduce the level of salt used in the formula. However, reducing salt in formulas is very challenging because of all the functional roles of salts in food. No other single ingredient performs all the functional roles of salt. It controls microbial growth, which is important for desired growth. So think about yeast leavened breads, where you want just the right amount of gas production to be reduced. If you look at the graph over on the upper right, this is an example of where we looked at proof times of dough. So it's telling us how much yeast activity we're getting. When we actually add no salt to the yeast, that would be the bar on the far left, you actually have the fastest proof time. The highest or slowest proof time is that salt, which is added at 100% of what the formula would be. And what we can also do is look at potassium chloride as a replacement, which is the two bars that are in the middle of that graph. And as you see, potassium chloride can be used to help with that control of the yeast gas production. When we also think about salt, the presence of salt also helps decreases or eliminates the growth of spoilage organisms and pathogens. Salt also alters the secondary and tertiary structures of proteins. In the case of meat, salt helps extract soluble proteins. It helps create emulsions of fat, water, and protein. And the ordered structure of these myofibril proteins of ham in the presence of salt is shown in the lower left microscopic photos. The emulsified structure helps retain the moisture in the fat, and it gives that desired taste and texture that peak consumers are looking for. The no added salt ham is in the lower right photo and doesn't retain moisture and fat and creates actually a tough, bland product. Lastly, and probably most importantly, salt is added from a sensory perspective. It provides a salty taste, flavor enhancement, creates desired texture and color. To demonstrate the complexity of reformulation, this table showcases the many ingredients that contribute sodium to meat products. Many of these ingredients only have one functional role, such as lactates and diacetates, which are used for preservation. In general, many ingredients have no or low sodium alternatives. However, they may be limited in use due to off flavors at high levels of usage. In addition, flavor can be significantly impacted if many sodium containing ingredients are substituted and used at the high levels at the same time. For example, potassium chloride is commonly used to replace salt, but it has bitter and metallic notes at high levels. So 100% replacement of salt by potassium chloride is virtually impossible. Over the decades, there have been more and more products reaching the market that are lower in sodium. This has been accomplished through reformulation, new product launches with lower sodium targets. Monitoring changes in the food supply is challenging due to the dynamics of the food supply. So new products are being launched all the time, reformulations are occurring, and some products are actually pulled from the market. In some instances, products are launched in a stealth manner, meaning that the food manufacturer isn't calling out the fact that they're reducing sodium. So it becomes challenging to understand unless you're monitoring sodium content over time, these types of reformulations with no claim whatsoever about reducing sodium. So this again makes it very difficult for tracking in the process, but fortunately many food companies are reporting progress in their sodium reduction journey. So if they make a public proclamation about reducing 25% sodium across the portfolio, for the next 5 years, they will actually give us progress and updates as we move along. But one tool to help monitor the changes is conducting market research. In the top graph of this slide, we see that in the last 18 months, prior to April 2021, there have been almost 1,300 products launched or reformulated with reduced sodium positioning. Of those products, nearly 1,100 of them contain potassium chloride, also known as potassium salt. So the good news about a potassium-based alternative is potassium enrichment, an underconsumed nutrient that helps mitigate the negative impacts of sodium on blood pressure for individuals with prehypertension and hypertension. These market launches have consistently grown year over year, indicating a potential change in the sodium content in the food supply. Namely, we anticipate a lower level of sodium available in the market. Research suggests that reduced sodium foods, new launches, the reformulations are being introduced into the market, resulting in decreased sodium within the food supply. Monitoring population sodium intake may give insights as to the effect of changes in the food supply. Similar to monitoring changes in the food supply, there are challenges in monitoring changes in population sodium intake, such as the method used to measure the sodium intake and the lag in time for data collection and analysis. In addition, the method for sodium intake analysis may actually even change within a particular monitoring program itself, again, adding more challenges. In the table on the left, Santos reported that the analytical methods for sodium intake varied from 24-hour urinary collection, dietary survey, spot urine, or combinations thereof, making it a little bit challenging to compare study to study. Of the 96 countries with initiatives in 2019, 25 reported a decrease in population sodium intake compared to only 12 in 2014, suggesting that changes in the food supply are impacting sodium intake. The ranges for reduction in some cases and increase for the sodium intake range from minus 29% to plus 3% in 2019 and minus 36 to minus 4.9% in 2014. Again, reiterating the fact that what we're seeing, what's happening in the food supply is actually having an impact on the sodium intake. A couple examples are on the right side, reporting progress, positive progress in China. looking at 12 provinces, they saw a decrease. The UK, some countries in there are also reporting a decrease, England, Northern Ireland, and Scotland. And here in the US, we're seeing a slight decrease, although if you look at the subpopulation of adults greater than 17 years of age, we actually saw an increase in sodium reduction. You know, the differences of looking at population versus individual consumption or intake. So in conclusion, we know that the government and non-government organizations continue to encourage food industry to decrease sodium content in the food supply. Many governmental strategy exists and involve voluntary or mandatory initiatives. Food reformulation is the most common means, but there are still many challenges faced by product developers to meet consumers' expectations, especially when it comes to taste. Salt, a source of sodium, has many functional roles, making it a valuable tool for the food industry and therefore extremely challenging to remove. And monitoring sodium reduction in the food supply is also challenging due to the market dynamics and data collection. There's also challenges with monitoring a population intake, clearly recognizing that new methods need to be generated for those last two. And however, but what we're seeing from the results, it suggests that progress is being made in reducing sodium in the food supply and population sodium intake on a global level. Thank you, and back to you, Naomi.
Thank you very much, Janice. We'll take questions at the end, so I'll go right on with our next speaker, who is Dr. Soo-Yoon Lee of the University of Illinois at Urbana-Champaign, and she's professor in the Department of Food Science and Human Nutrition. She will give us an overview of some guiding principles for the reduction of sodium in food. Sue?
Thank you, Naomi. Can everyone see my screen well?
Looks
yes?
good, yep.
Okay, great. Thank you. All right. Sodium overconsumption is a global issue, and as can be seen in this map that was created in 2010, a lot of the regions in the world exceed the WHO recommendation about 2,000 milligram per day, and it's ever so increasing. In light of the issues with high sodium consumption, in 2010, Institute of Medicine has published a report on the research needs on sodium reduction. And they have 3 pillars that they think are very important for research support, which are to understand how salty taste preference developed throughout the lifespan, and to develop innovative methods to reduce sodium in foods while maintaining palatability, physical properties, and safety, and to enhance current understanding of factors that impact consumer awareness and behavior related to salt reduction. As a food scientist, my main research focus has been to develop innovative methods to reduce sodium in foods, and for a majority of this presentation, I would be discussing what I've seen in the literature as well as some of my research. As Janice presented, approximately 77% of restaurant processed foods are the sources for sodium. If you look separately for the processed and packaged food, it comprises about 70% of source of sodium versus the home and restaurant foods 30%. And within the processed and packaged foods area, the top ones are breads and rolls as the source, and cold cuts and cured meats, followed by pizza, poultry, soup, sandwiches. Along with the products that provide the salt, when you look at the literature, the research that has been done in the past on salt reduction, you can see that the majority of research has been done in the category of milk, meat, and poultry category, primarily the processed meats, followed by the bakery product and dairy, namely the cheeses. When you look at the sodium reduction strategies that are reported in the literature, the number one strategy that has been used and published is the salt replacers, namely the potassium salts, potassium chloride. And then just salt removal, as Janice mentioned, that's one of the top ways to reduce salt, and without any adding mitigating strategies to enhance the palatability of the reduced salt product. And then the third category of salt reduction strategy would be flavor modification, which is a broad category which encompasses flavor enhancers such as monosodium glutamate, as well as congruent flavors using herbs and spices. For my presentation, I would like to discuss some salt reduction strategies that are very specifically aligned with the matrix of the food, because the characteristics of the food actually makes it different the way people perceive the salt. So, for example, in semi-solid food matrix such as cheeses and processed meats, the salt has to diffuse through the food in order for us to be detecting it as it dissolves in saliva. And in the literature, it has been reported that up to 95% of the salt may actually not be released from the food before swallowing. So it's in the food, we ingest it, but we don't actually perceive it. So there's a lot of research that can be done in how to manipulate the structure of the food so that the salt is released faster. In a solid food matrix, such as chips, where the salt is applied topically, you would have an instant salt perception from the surface of it. So the majority of the strategies that are reported in the literature is on the salt itself, the particle size and shape, as Janice mentioned, and also even microstructure of the salt. In addition to that, you can use salt replacers or flavor enhancers in this type of topical application. In liquid-based foods, such as soups and salad dressings, salt is dissolved completely in the food matrix. And so a lot of the strategies reported in the literature is chemical replacement, such as potassium chloride replacement or flavor enhancers, and also some textural and mouthfeel modifications, such as manipulating the viscosity. So if we look more closely into some of the categories here, let's first look at the semi-solid foods like cheeses and processed meat. And the question is, can we modify the structure of the food such that the salt is released faster from the food? So there's been several papers that has been published from one of the research laboratory at the University of Illinois, where I'm at. They use the solid lipoprotein colloidal food system, and they've been publishing since 2014. And they manipulate the structure of these model food system that is mimicking kind of a cheese system, because they use whey protein isolate as the protein source and anhydrous milk fat as the fat source. They vary the pressure of homogenization so that they have different particle size of emulsion, which then they heat up to gelate and to make the solid lipoprotein colloidal system. And they verify the structural differences using microscopic images, where the porosity and the tortuosity and the number of particle size differs by different processing methods and ingredients. They did not only measure the salt release in vitro, but also using sensory panel to see how the salt perception changes using different microstructures. And what they found was that indeed the saltiness perception is related to structural differences of these solid lipoprotein colloidal system, and that specifically, it's related to the porosity and particle size of the fat, because there's a significant relationship with increased serum release with the saltiness and these structural differences. They also found that non-fat versus fat-containing lipoprotein colloidal system was really different in terms of saltiness perception as well as textural perception. So something to consider when you're thinking about and comparing reduced fat products such as in cheeses. Moving on to the topical application of salt, such as chips and snack foods, the main strategy that is used in the literature is, again, the particle size and shape of the salt manipulation, as well as manipulating the microstructure within the salt, and then adding, for example, flavor enhancers, or even using congruent flavors using spices and herbs. For this, I would like to present two of my studies that have been recently published in the Journal of Food Science, and we used potato chips and puff rice. Here, the strategy that I used was flavor enhancers. So flavor enhancers such as monosodium glutamate, as well as disodium inosonate and guanylate are a great source of strategy for sodium reduction, because they not only provide additional salty taste, but also enhance the savory, which then the palatability and fullness of the food increases. These flavor enhancers are generally recognized as safe, and they occur naturally in products like Parmesan cheeses, tomatoes, and even breast milk. So the aim of the study that we conducted was to have these flavor enhancers and reduced sodium product, and do the consumer liking tasting in blind situation, and then followed by ingredient information session, where we're seeing if the liking changes if we provide the information of the ingredients, and then also ingredient information with education. So the panelists will come and do a blind tasting of these products. And then after 5-minute break, they would have the information given to them for each product, with reduction of sodium and also added flavor enhancers. And then following that session, another day, they would come in and do the informed with education session and conclude with demographic questionnaire. The educational piece was this as an entirety of it, and it composed of the need for sodium reduction due to health issues, as well as the FDA guidelines that was published to have sodium reduction up to 50% in various prepared food categories, as well as if you reduce the sodium, the likability decreases. And then the final piece of the educational paragraph included the safety of MSG and I plus G, as well as how they can mitigate the loss of palatability in reduced sodium products. So the findings were that flavor enhanced samples in a reduced sodium product was actually rated the highest, which was great, in a blind condition. And to our surprise, that ingredient information actually did not reduce the liking. It increased the liking of these reduced sodium and savory products. So in fact, the education part wasn't even necessary. It either maintained the liking or increased the liking very slightly from the informed condition levels. So in the final category, the liquid food, the soups and sauces and salad dressings, the main ways the salt is reduced is using salt replacers. So it's mainly the chemical modification. And then some studies show the viscosity changes that actually relates to palatability mitigation of reduced salt products. And then some studies also show that flavor enhancers definitely aid in these liquid food product, because it's also chemical modification, as well as using herbs and spices and congruent taste flavors. There are a couple of studies that we have published in this area, the liquid food system, with soup, where we had soup with varying levels of herbs and salt, and we showed that ad libitum addition of salt was significantly decreased when we had significant increase in herb. Also, in a retorted process soup system, we have shown that varying levels of herbs can mitigate the reduction of liking in reduced sodium and reduced fat products, and that there's a relationship between reduction of salt and fat and herb, and how you can manipulate those ingredients to make sure that you aim for a certain reduction without losing consumer acceptability. To conclude, successful sodium reduction strategies in terms of the food scientist's point of view should be aligned with the food matrix and its characteristics. And some examples that I gave in the presentation is structural modeling for semi-solid foods such as cheeses and processed meats. And then for topical application using flavor enhancers, and then for liquid foods using chemical modifications such as flavor enhancers and salt replacement using potassium chloride. Learning all of this, I think it's very important to realize that there are many ways to reduce salt in the food system, and that that understanding the food characteristics is very important to be successful. Thank you.
Excellent. Thank you very much. And now we have Mary Murphy, who's a senior managing scientist at Exponent. She will tell us about a modeling study that was funded by the IFAN Sodium Committee, specifically examining the effect of one of the most commonly used sodium replacers, potassium chloride, on sodium and potassium intakes. Mary?
Thank you, Naomi. Can everyone see my screen? Is that,
Looks good.
Good? Okay. I will turn off my camera and proceed. So thank you. Today I will be talking about use of potassium-based sodium replacers, what happens to nutrient intake. I'm going to be presenting results from a modeling study that we recently completed. Findings have all been published in AJCN. So, okay. So it is well known that sodium intake greatly exceeds recommendations, as we've heard today. Most sodium in the diet is from sodium in commercially prepared and processed foods in the form of sodium chloride. A primary objective in reducing sodium intake is to lower blood pressure and risk of cardiovascular disease. One strategy to reduce sodium in the diet is to replace sodium chloride with potassium chloride. Previous modeling studies provide insight on the potential impact of potassium chloride replacers on sodium and potassium intake. We are not aware, however, of any such modeling studies that have been conducted in a US population or studies incorporating feasible and practical potassium chloride replacement with consideration of specific food type. Potassium chloride replacers may impart a bitter taste, as Janet noted, and due to this and other factors, the same level of use across broad food categories may not be a reasonable assumption. The purpose of our study was to quantitatively estimate changes in intakes of sodium and potassium by the US population, assuming use of potassium chloride in place of sodium chloride in top dietary sources of sodium, where dietary sources of sodium were identified using food categories aligning with FDA's 2016 draft categories for voluntary sodium reduction. The dietary intake data that we used in our modeling study were data from day one recalls collected in NHANES. We used 2 data time points in our modeling study. Today, I'll just be focusing on results based on the 2015-16 NHANES data, which were the most current data at the time of our analysis. The modeling study was conducted as a 5-step process in each NHANES survey period. I'll briefly review each step of that process now before presenting results. Step 1 of the study was identifying total sodium intake by the US population. Step 2 was then identifying top food sources of sodium. The food sources of sodium in the diet were identified based on categories developed by FDA in 2016. In their 2016 draft guidance, FDA identified approximately 150 food categories with target goals for sodium. As part of their work in developing the draft guidance, FDA mapped all USDA food codes in NHANES into categories of similar foods. Target categories represented categories for which sodium reduction goals were set. These are foods generally corresponding to processed or prepared foods. Non-target categories generally represent foods with only naturally occurring sodium. We refer to all of the food categories used for the NHANES mapping as the FDA voluntary sodium reduction categories. This figure shows the top 20 ranked food category sources of sodium in NHANES 2015-16. The total intake of sodium from the diet in this time period was roughly 3,400 milligrams per day. The top-ranking individual categories contributed approximately 40 to 245 milligrams, or 1 to 7% of the total dietary sodium intake. You can see the top-ranking source of sodium was grain-based dishes. Many other mixtures, including tacos and burritos, meat and poultry-based dishes, pizza with meat, soup, egg-based dishes, and vegetable-based dishes were among the top sources. The solid green bars here represent the target categories, and the shaded bars, just 2 of them, represent non-target categories. The 18 solid bars are the categories that we used in our modeling. They account for slightly less than 50% of sodium intake. Step 3 in our study was identification of ingredient sources of sodium in foods in those top-ranking target categories, and specifically sodium present as sodium chloride. We disaggregated foods in the top 18 categories into their component ingredients. We categorized each food ingredient by source of sodium into one of 3 categories. The first category represented food ingredients with no added sodium from sodium chloride. These were things like milk or fruits and vegetables, or ingredients such as sodium bicarbonate. Foods with low or reduced sodium comprised the second category, and the third category represented ingredients that contained some added sodium chloride. These were the ingredients in the top 18 categories, representing primarily breads, condiments and sauces, dairy products, select fats, processed meats, soups, and miscellaneous foods, including spices. Table salt was an ingredient in some mixtures and was included in the category of sodium-containing ingredients. We categorized all of these sodium-containing ingredients into approximately 60 food ingredient groups and estimated the percent of sodium as sodium chloride in each group. Step 4 in our process was then identifying the amount of feasible and practical replacement of sodium chloride with potassium chloride in each of those roughly 60 categories. In this step, in our study, feasible and practical replacement of sodium was defined as replacement that would maintain key roles of sodium in foods, for example, technical function, food safety, shelf life, consumer acceptance, while using existing technologies and using standard potassium chloride. We designed and conducted an expert elicitation to systematically identify feasible and practical potassium chloride replacement of sodium in sodium-containing ingredients. To complete the expert elicitation, we engaged 20 experts from academia, industry, and consultants, and engaged them in structured phone interviews. For each food ingredient group, we asked each expert to provide estimates of the lowest, highest, and most likely feasible and practical replacement of sodium chloride with potassium chloride. This figure presents the estimates of most likely feasible and practical sodium replacement across the nearly food categories based on the data gathered in the expert elicitation. For the feasible and practical scenario considered most likely, mean replacement of sodium was about 14 to 35% per food ingredient group. So lastly, step 5 of our study was modeling replacement of sodium from sodium chloride with potassium chloride. In this step, we estimated predicted concentrations of sodium and potassium in foods under 4 models. We assumed total replacement of sodium from sodium chloride, which is unrealistic, but provides an upper bound on potential sodium reduction and potential increases in potassium intake. We also assumed feasible and practical replacement based on most likely replacement, with those estimates of lowest and highest replacement providing a range around the most likely estimates. Modeled estimates included sodium intake, total potassium intake, and intake of the sodium potassium ratio. So finally, we're at some results. This slide presents results of the modeling in the top 18 food sources of sodium for the population ages 2 years and older. In the scenario assuming total replacement of sodium chloride with potassium chloride, sodium intake dropped 41% to approximately 2,000 milligrams per day, while potassium intake increased 75% to approximately 4,400 milligrams per day. In the feasible and practical models, which are realistic scenarios, sodium intake dropped 9% to about 3,100 milligrams per day, and potassium increased about 16% to a level of roughly 2,900 milligrams per day. But FDA's short-term sodium reduction goal is 3,000 milligrams per day, which is therefore consistent with the sodium intake modeled in the feasible and practical scenario. FDA's long-term sodium reduction goal of 2,300 milligrams per day was achieved only in the total replacement scenario, which as I noted, is an unrealistic scenario. To understand potential shifts in sodium and potassium across subpopulations, we also examined intakes for individuals based on demographic factors including age, sex, race ethnicity, and household income. Today, I'll review results for subpopulations of adults by sex and subpopulations based on race ethnicity. This slide shows results for adult males by DRI age ranges. On these slides, you'll see baseline estimates in solid green for sodium or blue for potassium, the predicted estimates representing the most likely feasible and practical replacement models are represented by the lines with the bars with the diagonal lines, and the predicted estimates representing total replacement are the light shaded bars on the right of each set. You can see that sodium intake in the youngest subpopulation of adult males is approximately 4,400 milligrams per day, but this sodium intake declines with age, while potassium intake is a little more consistent and ranges between roughly 27 and 3,100 milligrams across these four age groups. In the total replacement scenarios, sodium intake was predicted to decline 44 to 45% among young men, 42% for men 51 to 70 years, and 40% for men 71 and older. The concurrent increases in predicted potassium intake range from 90 to 65%. Again, these are not realistic scenarios. In the feasible and practical replacement scenarios, sodium was predicted to decline between 8 and 10%, while potassium intake increased 13 to 19%. In the feasible and practical scenarios, sodium intake remains above the 2,300 milligram target. Potassium intake, if you notice, in the feasible and practical scenarios is comparable to the adequate intake level of 3,400 milligrams per day for men, and that's indicated by the yellow bar. This slide shows comparable results for adult females. As expected, sodium intakes and potassium intakes are lower among females. The baseline intake of, though you'll see that the shifts in potassium and sodium intake follow very similar patterns as we saw for the men. In the feasible and practical replacement scenario, sodium was predicted to decline between 8 and 9% for women, while potassium increased 12 to 17%. Among women, sodium intake was at or above the 2,300 milligram goal, indicated by the orange line, while potassium intake for women is, the AI is 2,600 milligrams for females, and you can see our feasible and practical levels are at or below the AI. Predicted intakes of sodium and potassium were also examined by race ethnicity across the US population, ages 2 and older. In this total replacement scenario, sodium intake was predicted to decline 39% for subpopulations of non-Hispanic white and non-Hispanic Black individuals, and 47% for subpopulations identified Hispanic or race ethnicity other than these three groups. So you can see there may be some differences by race ethnicity. In the feasible and practical replacement scenarios, though, again, sodium was predicted to decline between 8 and 10%, while potassium increased 14 to 19%. Lastly, we also looked at the ratio of sodium to potassium in our models. The ratio dropped from 1.5 at baseline to approximately 1.1 in the model, assuming feasible and practical replacement. You can see the results for the population 2 and older, and our subpopulations of adult men and women are very similar. So in summary, these findings indicate that feasible and practical use of potassium chloride as a replacement for sodium chloride in the top sources of sodium modeled here could result in reductions in sodium intake, with daily intake lowered to roughly 3,000 milligrams per day for the US population ages 2 and older, while maintaining mean potassium intake in the range of recommended intakes for apparently healthy population. The resulting sodium intake is consistent with the short-term reduction goal targeted by the FDA. As shown in analyses by subpopulation, baseline intakes of sodium and potassium differ across subpopulations, though the trends in predicted intakes presented as percent decrease in sodium or increase in potassium were generally consistent. The replacement of sodium chloride with potassium chloride in select foods provides a strategy to help lower the US population's intake of sodium. Implementation of additional strategies, however, will be required to reach reductions in sodium intake consistent with long-term sodium reduction goals of 2,300 milligrams per day. With that, I would just like to also note that our study was recently published. The full results are presented in the paper and the online supplemental material. Additionally, all the data files that we developed to conduct the study are freely available on the Open Science Framework website where the study was registered. And I would just like to thank all of the individuals who helped complete this study. Thank you.